Hi everyone, I am Linfang Zheng. I'm excited to introduce our latest CVPR work, GeoRef, which focuses on category-level object pose refinement. Category-level object pose includes the object's 3D translation, orientation, and 3D size. Accurate object poses are crucial for applications in autonomous driving, robotic manipulation, and augmented reality. In this work, we address the challenge of category-level object pose refinement. Given the point cloud of a target object, an initial estimation, which may not be accurate, and the shape prior, our goal is to estimate the relative pose between the ground truth and the initial pose, ultimately achieving high accuracy object pose estimation. Typically, this refinement involves iteratively comparing the transformed shape prior with the input point cloud. However, due to significant shape variations within a category, the target object and the shape prior often differ in shape and size, making relative pose estimation challenging. Existing algorithms do not effectively address this problem. To tackle this, we propose a novel architecture for category-level object pose refinement. Using the initial estimation, we transform the shape prior and apply our HS feature extractor on both the target object and the transformed shape prior for feature extraction. The HS feature extractor captures local and global geometric information using a graph convolutional layer and aligns geometric features with learnable affine transformations. We then introduce a novel cross-cloud transformation strategy, which mixes information from the two inputs, allowing the neural network to better understand the pose difference between them. After obtaining the global information, we leverage both the feature of the target object and the shape prior to accurately estimate the relative pose and size. We conducted extensive experiments to validate our method. In ablation studies, we confirmed the effectiveness of each proposed strategy. Incorporating shape prior information in pose estimation branches increased the baseline performance by 2.4% on the 10° 2 cm metric. Using the HS feature extractor significantly boosted performance, with several metrics improving by over 6%. The cross-cloud transformation further enhanced our model, with the highest improvement reaching 10.5%. Our experiment also demonstrated robustness to different shape priors and initial estimations. While the baseline failed to refine some initial poses, our method consistently improved them. We also tested the generalizability of our approach. Training with only 2% of the training set, our method outperformed the state-of-the-art baseline. Our refinement results show substantial improvements in initial pose estimations, with the highest improvement being 39.1%. Even with a weak initial pose estimator, our refinement outperformed the state-of-the-art pose estimators. On the Camera 25 dataset, we observed similar results, significantly improving initial pose estimation and outperforming state-of-the-art methods with just 2% of the training dataset. Here are some qualitative comparisons between our method and the baseline. The ground truth is shown in white lines, the baseline is in blue lines, and our method is in green. Note that for symmetric objects, the estimated rotation is considered correct if the symmetric axis is aligned. As you can see, our method performs better, especially for complex-shaped objects and even when part of the object is occluded. For more details, please visit our project page. You can also find more of my work on my personal page if you are interested. Thank you.